Mm. Hello, hello, hello. Yeah. Mm. Okay. For some reason, the video capture just inexplicably stopped working, but I guess that's fine. I guess I don't need it. Um. Okay, fine, whatever. Let me pull up my stream just in case just to see if it's broken. Okay. All right. Fine. Okay. Um. Okay. I guess I'll wait for us, or maybe I won't. I'll just go. I'll just plow ahead. All right. Let's talk about groups then. All right, groups. Um, I suppose there's a few things that I want to talk about. So I want to talk about uh, finite groups. I want to talk about the Mobius group. I want to talk about Sn and An, why A5 is simple, and maybe um, some stuff miscellaneous, I'll call it, like Lagrange and so on. OS. Okay. And that should suffice, I guess. Let me have a look, see if anyone's here. All right. Okay. Um. Okay. So I guess the first thing to discuss is I guess one of the most important theorems that we can begin with. I'm gonna assume you know what a group is and like what a homomorphism is. Um. So okay, what about Lagrange? Lagrange. What did he have to say about groups? Well, if we have a finite group G and some subgroup H, then the order of G is just the order of H times by the number of cosets that we have, so the index of H in G. Now, oh, you forgot what a group is? Okay. Oopsie. Okay. So, what is a group? That's a good question, I guess. Um, a group. I guess we can start here then. A group, G, is a pair. So you have a set G, and you have an operation times, where times is just it takes in two elements and outputs one. So, for example, like addition or multiplication or whatever in like the natural numbers, no, not natural, in like the integers would be an example. This is just a binary operation. Notably it's closed, right? So what do we need from this binary operation? Well, we need that there exists some E, so we need an identity element such that for all G and G, we have that EG is equal to G. What else do we have? We have that for all G in G, there exists some G inverse such that G inverse is equal to G inverse G is equal to E. So we have inverses too. And we have associativity. So G times by H times by, I don't know what's next, F is equal to, I forgot what the standard one is. What's the third letter that people use? I don't remember. I'll use F. So the order of what of how you do the operation could matter. Like, it's not necessarily true that GH equals HG, but we're associative. So it doesn't matter if you do G times by H times F, or if you do G times H first, and then you times by F on the right. It's the same thing. And the fourth one is what I was saying before, is closure. So for all G1, G2, G1 times by G2 is in G. So you can think of it like this, right? Say say you have sorry, I probably can't really keep up with the chat, unfortunately. If I say something really outlandishly terrible, then please do ping me in the Discord server. What was I going to say? You can think of it like this, right? Say we want to do algebra. This is what. Say we wanted to solve 2x plus 1 equals. Oh no, sorry, that's bad. Say we want to solve x plus 1 equals 10, right? What do we actually have to do to get x? Well, firstly, we need the existence of minus 1. We need something to cancel this out. And speaking of cancelling out, we need, even before that, we need there to exist a 0, because we need the idea of cancelling out to make sense, right? So if we minus 1 on both sides, then we get that x is equal to 10 plus minus 1. I should say x plus 0 is equal to 10 plus minus 1. And now we want that this is in our group G. So we want that this is a number. Otherwise it wouldn't really work. So you can think of these as like the minimum axioms that we need in order to do algebra. And if you like started adding stuff, then associativity becomes necessary too. If you start doing, I mean, if you don't have associativity, you have to be really careful with brackets. Now, the reason I deleted the 2 is because that would require multiplication, which we only have one operation in a group. So, you know, obviously people have studied rings, which is where you have what's it called? Obviously you have rings where, you know, we can do multiplication, and fields where you can have multiplicative inverses as well, and you study how that works. But in groups, it's just one operation. So what are like the minimum axioms required for us to be able to do algebra with a set G and an operation times, a binary operation, and then you study it. So, I mean, an example of a group would be, say, I don't know, a simple example would be just the integers with addition, right? Because if you add two integers, a plus b is going to be in the integers, so we're closed. A plus b plus c is equal to a plus b and then plus c, so that's good. For all, well, a plus 0 equals a for all a. So we have an identity element 0, that's good. And for all a, there exists a minus a such that a plus minus a is equal to 0. So we have inverses too. So the integers with addition are a group. But notice that the natural numbers with addition are not a group because there's no inverses. Or you know, if you don't include 0, there's also no identity element. In a similar vein, the integers with multiplication are also not a group because we have no inverses there as well. So there's a couple of examples, hopefully, to get you in the mood. Hopefully that is what's it called? Whetted your appetite. Now, the first thing that I wanted to discuss, right? The first thing I wanted to discuss was Lagrange. What on earth did this old Lagrange fella say? What is the Lagrange's theorem, so to speak? So, entropy can point out if there's an infinite version. I imagine, I think like this does make sense for infinite groups, but I'm just going to talk about the finite version. But yeah, they're definite. I mean, I know for a fact that there is an infinite version. I just can't remember what it is, to be honest. But anyway, for a finite group, so say we have a group which has n elements. So for a finite group, G, and H being a subgroup of G. Now, subgroup is like a subset of G, which is a group, basically, is the simplest way to describe it. I think that is actually like true, yeah, with the same operation, of course. Yeah, it's a subset of G, which is a group in its own right. Yes, yeah, that is true. Okay, now, we have that the order of G, which is the number of elements in G, can be calculated as the number of elements in the subgroup H times by the number of cosets. Now, you might be wondering, what on earth is this thing? What is a coset? Well, okay, we'll derive this. So fear not. Let's say you have some subgroup H of G, right? Then a left coset is a set of the form. Is it a group? No, it's not. It doesn't have E. Oh no, maybe it does. Anyway, this is not precise, the most precise definition ever, but whatever. Left coset is a set of the form GH, which is equal to the set of all GH. So basically, it's just like the set of all things. It's the set that you get by multiplying everybody in H on the left by G. For example, if you take a look at the integers, oops, can I not? Wait, why can't I go below? What's going on? Is this like some free version where I can't go as low as I like? What the hell? This board is tiny. Oh, actually, no, it's not. Oh, I just started really low down. Okay, let's talk about cosets here. So, for example, if you have the coset, if you're given like the integers, we could have the coset 2z, where you just multiply all the integers by 2. So this would just be blah 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 minus 2, 0, 2, 4, da 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 da, like so. Right? So cosets are just like we take everybody in our subgroup, in this case the integers, and we multiply on the left or the right if you want, but typically on the left, by some element of our group, and we look at the set that arises from that. Now, all right, let's see if okay, now, all right, let's let's proceed. So if okay, so we're looking at this coset. Oh yeah. Now, here's the thing about cosets, right? given some subgroup H of a group G, the cosets partition G. So what does that mean? Firstly, that means that if you take the union of all of the cosets, so all of the different possible cosets, you take the union and you get G. So you get your group back by taking the union of all of the cosets. But the second property is that if two cosets have any intersection, so if G1 intersect G2H, G1H intersect G2H is not the empty set, then this implies that they're the same thing. So what does this mean? This means that each coset is distinct. So if your group G is like this box here, your cosets, partition the group, but like in a disjoint way. So this could be coset number, this could be H, this could be G1H, this could be G2H, and this could be G3H, like so. So like all of the cosets, they break the group apart into different pieces, and they're all disjoint, so there's no intersections between these different parts. All right. Now, there's another there's more good news about these cosets, and that's that they're all the same size, which is amazing because why are they the same size? Well, for all G in G, whoopsie daisy. We have a bijection from H to GH, and what does it do? It just sends any element H to GH. And this is a bijection because, well, obviously it's a surjection, right? By definition, it's a surjection. And why is it an injection? Well, if you had GH1 equal to GH2, because we're in a group, we can multiply the left by the inverse of G to get that H1 equals H2. So all of these cosets are the same size. So actually I can make this picture more precise. I can say, look, say we have 5 cosets. Well, they're all the same size, so it'd be 4 cosets. It'd be G1H, G2H, and G3H. And those are all my cosets. And this, like, visually automatically tells us Lagrange's theorem, right? Because if you look at it, if you're in a finite group G, if we have G, the size of G is, because we're disjoint, we can sum over all of the cosets GH. Whoops, I didn't like that. Of the size of GH. But these are all the same thing. So this is just equal to the size of H times by the number of these cosets, which we denote like this. And so Lagrange's theorem holds. And this is an amazing theorem. This tells us loads of important things. For some reason, this board is really bad. Like it's really, no, it's a good board. I just mean it's really small. I seem to have used up my whole board. Why would they not give me infinite space? Does anyone know a better whiteboard that I can transfer to? I take care differentiating between left cosets and cosets. Left and right cosets can have non-trivial, non-full. Oh yeah, that's a good point actually. Yeah, that's a good point. I guess, yeah, I should say left cosets partition G. Right, yeah. I guess if we're not in a, yeah, okay, yeah, that's a good point. All right, let me try find a better whiteboard because this one is small. So we just proved Lagrange's theorem, I'm going to move on to some applications once I find a better whiteboard. Online whiteboard. Yeah, drawing, let's say. Let's have a look. Which one is good? Maybe this one, Whiteboard Fox. Okay. Oh, you can have my data. Otherwise, no. Only view my drawing. Create whiteboard. Okay. Is this infinite? Oh no. What happened? I just got rid of the. Okay, we have an annoying ad in the right, but oh well, whatever. That's fine. Okay. Anyway, so where were we? We had Lagrange's theorem. So we have that G, the size of G, is equal to the size of H times by the number of cosets that H forms in G. This is called the index of H in G. Now, what's a great application of this? A really useful one is that if H is a subgroup of G, that implies, we're working in finite groups here, this implies that the size of H must divide the size of G. Now, why? Well, because this is an integer, so there you go, it follows. That's pretty much it. Now, a good corollary from this is that if if the size of G is prime, then G is equal to the cyclic group of order P. And what's the cyclic group of order P? Well, you can think of it just as like the integers mod P, right? So it's just the numbers 0, 1, 2, up until P minus 1 with addition mod P, basically. Now, why is this true? Well, consider a non-trivial element, G and G. Well then, if you look at the subgroup generated by G, which is defined as just, the set of all G to the n, where n is a natural number. So like, it's just E, G, G squared, G cubed, right? Until we hit the order whenever G becomes a, let's say P minus 1, right? So it's just this set. Well, this forms a subgroup. You can easily check that. But no. This forms a thingy. Let me move. Yes. Okay, I want to move. All right. Yes, this forms a subgroup. Yes, but we know that the subgroups, the size of the subgroups, have to divide the order of G. So we know that the order of this subgroup has to divide the order of G, but that's just P. But P is prime. So this means that because this is non-trivial, this is not 1. So this means that the size of G, the subgroup generated by G, is equal to P. But the whole group is of size P. So so that means that G is equal to the group generated by G. But this is precisely the definition of the cyclic group of order P. Right? So in fact, we can classify groups of prime order very, very easily, right? They just, if you're prime, you're CP, that's it. Not in the bad way, in the group theoretical way. All right, now, okay, that's a nice little corollary. Did I have anything that interesting to say about Lagrange? I mean, there's plenty to say. You can prove some number theoretical stuff from Lagrange as well. But yes, okay. All right, now, I think the next theorem I'd like to discuss is the direct product theorem, actually. This one comes in handy sometimes. Direct product theorem. Right? What does the direct product theorem say? This says, again, oh, maybe we're not even working on it. Okay, anyway, whatever. If we have a group G, right? So we have a group G, and we have H1 and H2 are both subgroups of G. Then, if the following are satisfied. So firstly, H1 and H2, the only bit they intersect is E, is the identity. They don't intersect anywhere else. Secondly, if any element of G can be written as H1, H2, G equals H1, where H1 and H2 are elements of H. And thirdly, for all H1 in H and H2 in, for all H1 in H1 and H2 in H2, we have that they commute. So among themselves, they commute. Then we can simply say that G is isomorphic to H1 cross H2, where this is just the set of all pairs H1, H2 under addition or whatever the thing is, where H1 is in H1 and H2 is in H2, like so. All right, now how do we prove this? Well, let's have a look. I actually don't really remember, but my first thought would just be to define a map from H1 cross H2 into G. And what does it do? Well, it takes in a pair, H1, H2, and the most natural thing to do would just be to output the product, right? So we need to show that, firstly, we need to show this homomorphism. So I'm going to call this map phi, because that's my favorite Greek letter to use for this type of thing. So if we have phi of H1, H2 times by H1 primed, H2 primed, a homomorphism, by the definition of a homomorphism is that this is equal to phi of H1, so I'm going to put a question mark here, phi of H1, H2 times phi of H1 primed, H2 primed, like so. Right, so we need to show that this is true. I think there's probably some deep, there's definitely more deep reasons than just this has turned out to be useful as to why you should exactly define your homomorphisms like this. I guess you just want to preserve the structure. You want to look at structure preserving maps, whatever. I digress. So we want to show this, and then we want to show it's bijective, and then we're done. So, all right, let's have a look. Let's just dive in. What's the definition of multiplication in our group? Well, you just multiply element wise. So this is equal to phi of H1 primed, comma H2 primed, like so. And this is equal to, now we can plug in the definition, H1 primed, H2 primed. Now, this is equal to H1 primed, H2 primed. Why? Why? Well, firstly, we have associativity, so we can multiply these guys in any way that we want. When I say any order, I don't mean we can just swap the elements, but I mean I can do H1 primed first, and then times on the left by H2, H2 prime, or I can times by this guy on the right and then times the left, or what I'm doing here is I'm multiplying in the middle first and then proceeding. Well, we know from our third axiom, or it's not axiom, by our third condition, that the elements commute. So H1 and H2 commute with each other. Or sorry, H1 primed and H2 commute with each other. So we can simply just swap them. But now, again using the associativity, we can put these guys into pairs. But this is just phi of H1, H2 times by phi of H1 primed, H2 primed, like so. All right, perfect. Okay, so again, I mean, that also is a nice example of why associativity is really important to have. So, all right, yes, good. Okay, now, this is a homomorphism. Surjectivity follows at once. But because by the condition that we had, we immediately have that any G can be written as H1, H2. So surjectivity follows immediately. We need to show injectivity. How about injectivity? Well, let's have a look. So what would be the best way to show injectivity? Can we just go full steam ahead? And I don't think we can. I think the best way to show injectivity would be to show that the kernel is trivial. Or maybe, let's see. Yes. It would be to show the kernel is trivial. And I'll talk about this later, but let me just proceed. I should have, okay, yes, I should have done this first, but okay. I claim that the kernel of phi is just EE, like so, right? Okay, why? Well, if phi of H1, H2 is equal to E, then this implies that H1, H2 is equal to E by definition, but this implies that H1 is equal to H2 inverse. Okay, now we have an issue. That means that H2 inverse is in H1, but because H1 is a subgroup, this means that H2 is in H1. That's not good, because that means that H1, that means that H2 is in the intersection, because it's in H2 by definition. But that means that necessarily that E is equal to H2. So H2 is in fact the identity. But if you plug that in, you immediately see that H1 is also the identity. So indeed, we know that the kernel of this homomorphism is precisely just E. And so that means that phi is injective. I'll talk about why in a second. And so we're done. That means phi is an isomorphism, which implies that G is indeed isomorphic to H1 cross H2. Now, a nice corollary of this, before I talk about the kernel thing, is quickly that if we can get a version of Chinese remainder theorem from this, which is that if M and N are coprime, then CMN is isomorphic to CM cross CN. And the way that you do that is by considering, you look at CMN and you consider like the element of order M, and you look at the subgroup generated by that, and you look at the element of order N, and you apply direct product theorem. And you can show the various conditions by basic number theory. Like you can use Bezout's lemma or whatever. So you get Chinese remainder theorem as a corollary. Now, what was I going to say? I was about the kernel thing. Well, I'm going to assume you guys know what the kernel is, or All right, let's have a look. Okay, if we have a homomorphism phi from G to H, I claim that phi is injective if and only if the kernel of phi is simply just trivial, is equal to E. Why? Well, one direction is easy. That is, if phi is injective, so let's go this way first. If phi is injective, then phi of phi of G being equal to E, well, immediately we know that G is equal to E. Sorry, okay. We know that phi of E is equal to E because phi is a group homomorphism. You can show this, that phi of E is equal to, but by the way, this is the identity in H and this is the identity in G. Sorry, I should make that clear. So we know this, but phi is injective. So this means that phi of G also being equal to EH, well, this means that these two inputs must have been the same, which means that G has to be equal to EG. But that precisely means that the kernel is trivial. So that's one easy direction, is equal to EG. The other direction is also quite easy, but it's slightly more surprising. So let's now assume that the kernel of phi is equal to just EG. So it's just the identity. Then, if phi of H1 equals to phi of H2, sorry, yes, yeah. Then this means, there's a fire alarm, guys. I have to go. I'll see you guys tomorrow. I'm not going to restart the live stream.